Hi all. I made a severe and continuous video on integration last month or so, which was 6 hours long. And now I want to follow it up with another integration video. This time, 24 questions long. We'll be focusing here on trigonometry, integration by parts, and integration by substitution. So strap in, because it's gonna be wild. First question we have sine x secant to the power 4x. Now, one thing you have to know. Note, these trigonometric functions pair well with each other. Sine and cosine, they love each other very much. Secant and tangent, they love each other very much. And cosecant and cotangent, they love each other very much in the context of calculus. But remember, the derivative of sine is cosine, derivative of cosine is negative sine, right? Derivative of secant is secant tangent, and the derivative of tangent is secant squared. And similar with cosecant and cotangent, they have similar derivatives. So, suddenly, if you see sine and then secant in the same question, they have to ask, there has to be something else in here. They don't love each other very much. So what we have to do is to actually transform everything that is not sine or cosine, which is everything here, back into sine and cosine. Because the secant here looks kind of a sus, if you will. So now, let's try doing that. Sine x remains sine x because sine x is good. Then secant to the power 4x, we all know that is just 1 over cosine to the power 4x. Since secant is 1 over cosine dx. Now here we can see the full image. We have sine and then cosine. Sine over cosine, that sounds a little bit like tangent. So let's group that together. Sine x over cosine x. And then the remaining is 1 over cosine cubed x dx. Now from here, we can conclude that sine over cosine is indeed tangent x. And then cosine cubed x on the denominator, we know that is secant cubed x. And secant and tangent love each other very much. So why not put secant here as well? Nice. And from here, we can start seeing a picture. What is the derivative of tangent? That is, tangent. That is secant squared x. What is the derivative of secant x? That is secant x tangent x. So that's what we have to take note of. If we substitute tangent x, then we need a secant squared x dx. That would leave a secant x alone in there. So we don't want that. Right, I'll tell you what I mean. Here you go. And then there's a secant x here. Where does it go? It's going nowhere. So we're not going to use tangent. Let's use the other one, secant. So if we use secant x as the substitution factor, this means the derivative is secant x tangent x dx, which is du. Alright? So let's rearrange this together. Secant squared x here, and then secant x here. Oh, let me just put properly. Secant x here, and then tangent x here dx. This then becomes du. Let me erase this one. Alright. There. Okay. So, the secant x tangent x dx becomes du. So, put the integral sign in, put du here. Secant x becomes u, and there's squared here, so it's u squared. And there you go. That is just the reverse power rule, which we can get by doing u to the 2 plus 1 is 3 over the power 3. Let's see. And u is secant, so we know this is going to be secant cubed x over 3 Let's see. That's the answer. Very nice. Alright, next question. 2 plus cotangent squared x over cosecant squared x dx. Those are two things that love each other, cotangent and cosecant. So you can actually do that thing. But the problem is, the cosecant squared is at the bottom. The derivative of cotangent, we know that is negative cosecant squared x. But cosecant squared x is at the bottom, so it's not quite usable. And the derivative of cosecant x is negative cosecant x cotangent x, and as you see, no cosecant on the top, and producing cosecant on the top would create unintended consequences. So we could use again the sign trick earlier, which is to make everything into a sine and cosine thing. So here's what we're going to do. What we're going to do is to turn cotangent into, in terms of sine and cosine. Cotangent is cosine over sine, so this is going to be cosine squared x over sine squared x dx, over cosecant is 1 over sine, so this would be 1 over sine squared x. What we can do here is to multiply both the numerator and the denominator by sine squared x. And it is important that you have to multiply both the numerator and denominator at the same time in order to make this happen. So what happens then? The top becomes 2 plus cosine, nope, not 2. 2 sine squared x plus cosine squared x, then the x here, over the bottom just becomes 1. So that's cute. Next step. Sine squared x plus cosine squared x, we know that's 1. But there's an extra 2 here. So what we can do is actually to do this. So we can split the sine squared x into 2 parts. Sine squared x plus sine squared x. Because as we all know, 1 plus 1 equals 2. Then we just add cosine squared x here, and then the x. No over ones. That's easiest. Now, what do we do with this? We know this is going to be just 1. So our entire problem now is 1 plus sine squared x dx. So how can we derive? How can we integrate this? Remember, this one. I'm going to put this in another page. Cosine 2x is equals to cosine squared x minus sine squared x, correct? We can manipulate this in order to get sine squared x and cosine squared x separately. Let's try finding a sine squared x first. How can we do that? Fun here. If you multiply this by sine squared x, if you add sine squared x here, cosine squared x plus sine squared x, that is just 1. That's good. But we do have this discrepancy here, so it's not the same anymore. So we do have to subtract sine squared x in the same breath. So this becomes 1 minus 2 sine squared x, right? So in summary, we just added sine squared x and subtracted sine squared x in the same breath, and we got 1 minus 2 sine squared x. That is one of the trigonometric identities for the double angle identity of cosine. So now we can isolate sine squared x here. Let's put 1 minus cosine is 2x over 2. That is equal to sine squared x. If you isolate sine squared x here. Alternatively, you can also get 1 plus cosine 2x over 2 as cosine squared x. How neat. We're going to be using this, but keep also this in mind for later and for other applications. So, So we have sine squared x here. We can turn that into integral of 1 plus 1 minus cosine square, not squared, 2x over 2 dx. This technique is called power reduction. Power reduction. It's because from the power of 2, you go down to a power of 1. Cosine, this is just power 1 squared, not squared or cubed or whatever. So we reduce the power by half. But the consequence is you double the x. So sine squared x is the original one, and then there's 2x there. So that's good. Let's just fix all of this. 1 plus 1 half. We can separate this into 1 half minus cosine 2x over 2. So 1 plus 1 half is 3 over 2. Minus cosine 2x over 2. Now from here, we can just directly integrate this. But if you want to, we can substitute 2x to be equal to u. Just so this goes easier, you know. So 2 dx is equals to du, or dx is equals to 2 du, sorry, 2 du. There we go. 1 half, sorry. 1 half du. There we go. So now 3 over 2 remains 3 over 2 minus cosine u here over 2 times let's just put this in parentheses, times du over 2, or 1 half du. Let's just put everything 1 half to the other side. There's 1 half here, there's 1 half here. We can do 1/4 outside. And this becomes 3 minus cosine u du. What is the integral of 3? It's just 3u. So we get 1/4, don't forget about 1/4, then 3u minus cosine u, the integral of that is sine u. Is it true? What is the derivative of sine u? Is cosine u. So that's fine. So sine u. It's just positive. There you go. Now let's go back to the x world. It's from u. So from u, we go to the x. Okay. 1/4 here, then 3 times u is 2x, so this becomes 2x. And minus sine, and u becomes 2x here. Let's go back. This becomes 3 times 2 divided by 4, that and that becomes 2, so this is just 3 over 2x, right? Let me remove. Yeah, there we go. 3 over 2x, we know that. Right? Minus 1/4 sine 2x plus c. That's the answer. Alright. Question number 3. Sine 3x sine 6x dx. So this is the integral of that. For this one, we're going to be using a certain formula. Here's what we're going to do. Let's go back to another page. I should probably... Anyway, we know sine 2x, right? We all know that. Actually, no. We know sine a plus b. This is the addition formula. So what is the addition formula? Well, this is sine a cosine b, well, not beta, just b, plus sine b cosine a. Alright? And then sine a minus b is sine a cosine of negative b plus sine of negative b cosine a. Okay. In here, cosine of negative something is the same as cosine of positive something because cosine is an even function, meaning it is symmetric around the y-axis. So, sine a cosine b. And then sine is actually an odd function, meaning it is asymmetric around the uh, y-axis, and it's actually flipped. So this becomes minus sine b cosine a. And from there, you can add both the sine a plus b and sine a minus b to get whatever you want, sine a cosine b or sine b cosine a. But what we want is actually sine and sine, so these won't work. We need another one, cosine a plus b. We know this is cosine a cosine b minus sine a sine b. And for the cosine a minus b version, this is cosine a cosine negative b minus sine a sine negative b. Again, cosine negative b is just cosine positive b, so this is cosine a cosine b. And sine of negative b is just negative sine b, so this becomes negative of a negative is plus positive sine a sine b. And look, sine a sine b is what we're here for, so we can manipulate our so and so together. So how can we do that? Well, what if we did this? Cosine a minus b, parentheses so we don't get confused, minus cosine of a plus b. How about that? Well, we know cosine a minus b is cosine a cosine b plus sine a sine b. And then we have to make this negative here. So negative of cosine a plus b is negative cosine a cosine b plus sine a sine b. Cosine a cosine b, negative cosine a cosine b, this and that cancel each other out. This becomes 2 sine a sine b. If we want to remove the 2 and just have sine a sine b, we just have to multiply both sides by 1/2. So this becomes 1/2, let's just put there, cosine of a minus b minus cosine of a plus b. Don't put plus c in there, we're not integrating. So that's the formula we're going to be using. So let's go back. So this becomes 1/2 cosine a minus b. So this is a, this is b. So we get, let's integrate this. Put the integral sign here. And then cosine a minus b is cosine of negative 3x. A minus b is negative 3x. There we go. Minus cosine of a plus b, which is going to be 9x. And then dx. There we go. Now, how about this? Well, we know that cosine of something negative is going to be positive. So, this becomes 1/2, then the integral of cosine of positive 3x, even function, minus cosine of 9x dx. Now, I'm going to teach you a shortcut. If you want to use the substitution, you can do that. But the shortcut is this. What is the integral of cosine? That's just going to be sine, right? Derivative of sine is cosine, so the integral of cosine is sine, positive sine. And then, just put 3x here. And then divide by this. So divide by actually this. So it's just divided by 3. Then don't forget about the 1/2 here, right? Minus 1/2 times, we do the same thing, sine of 9x divided by 9, right? We just divide by this. That's why 9 is on the bottom, plus c. Simplifying this further, we get sine 3x over 6 minus sine 9x over 18 plus c. That is the answer. Good job. Just put that there. There we go. Question number 4. Okay. 1 plus 2 cosine x over 2 plus secant x. A classic. So how can we go about solving this? Again, uh, we have to recognize who loves each other in trigonometry. Sine loves cosine, secant loves tangent. There's cosine here and then there's secant here. They don't love each other very much. So what we're going to do is to turn this into something related to sine or cosine. So 1 plus 2 cosine x remains cosine x over 2 plus secant x becomes 1 over cosine x. Right? Secant x equals 1 over cosine x. That is, yeah. So what now here? Well, one good thing to do is to resolve the apparent complex fraction here. So we're going to be using the technique known as multiplying the numerator and denominator by the same thing. It appears a lot in mathematics, but cosine x multiplying both the numerator and denominator, review. So let's try not to actually distribute it, distribute the numerator. So let's just make it like this. Now, why didn't I distribute the cosine already? Wait, just wait a moment. This is gonna be fun. Alright, now we have to distribute the cosine here. So 2 times cosine x is, let's just put it here, 2 cosine x. Since this is positive, it's just add. And then 1 over cosine x times cosine x is 1. Do you see it? 1 plus 2 cosine x. And on the bottom, 1 plus 2 cosine x. Cancel, cancel. The integral becomes cosine x dx. I think we all know what that is. Sine x. Wait, we forgot plus e. There we go. From that thing, it just became cosine x and then the integral is just sine x. Cool. Cool, man. Number 5. Cotangent x over cosecant x minus sine x dx. Again, in here, cosecant, cotangent, they love each other very much. The problem is, there's the pesky sine x there. So what can we do in order to solve this? How about this? We could use the trick earlier to make it a sine x and cosine x, all of that. We could use that. But for this one, I actually want to multiply both the numerator and the denominator by cosecant. Why? You'll see. Right? The top becomes cosecant x, cotangent x. We love to see it, right? The bottom becomes cosecant squared x minus sine x times cosecant x is 1. Since cosecant x is 1 over sine x. And I think we can see something very similar forming here. What is cosecant squared x minus 1? We know cosecant squared x minus tangent, no, not tangent, cotangent squared x equals 1. We know that. Let's put this here, let's put that here. We get cosecant squared x minus 1 equals cotangent squared x. And boom. Cosecant squared x minus 1 is cotangent squared x. So let's replace it. This becomes cosecant x cotangent x over cotangent squared x. Alright. So from here we can just cancel this one. We get cosecant x dx over cotangent x. And now we reach an impasse. I mean, how can we even get solving that? Well, now's our chance to use the the trick I taught you. Turn all of this into something related to sine or cosine. Cosecant is 1 over sine, so we're using 1 over sine x there. And cotangent is cosine over sine, so cosine x over sine x. And we have a complex fraction again. We just have to do the trick called multiplying the numerator and the denominator by the same thing. In this case, sine x, to remove the denominators. The numerator denominators and the denominator denominators. Anyway, top becomes 1, bottom becomes cosine x. 1 over cosine x, that is just secant x. And I think we all know the derivative of, the integral of secant x. Ln of a secant x plus tangent x plus c. There we go. Now, you might ask, what would happen if this cosine, this initial thing, we just straight up did the sine and cosine thing on it? So let's see. We can experiment. So you write the question here. Minus sine x. Let's turn all this into cosine or sine. So cotangent becomes cosine x over sine x, right? And cosecant becomes 1 minus sine x. And then sine x is just sine x. Complex fraction appeared. Let's turn this into something easier to understand, which is which uses a trick called multiplying the numerator and the denominator by the same thing. Cannot stress that enough. It's a very useful trick. And then the numerator becomes cosine x since the sine x's cancel each other out. And then the denominator becomes 1 over sine x times sine x is just 1 minus sine x becomes sine x times sine x becomes sine squared x. And would you look at that? This is just cosine squared x. So we get cosine x over cosine squared x. Cancel, cancel. This becomes 1 over cosine x dx. Or secant x dx. And as we can see, we reach the same conclusion as before. And the answer is still the same, ln of secant x plus tangent x plus c. So no problem there. No problem, man. Alright, question number 6. Integral of sine to the 4. Sine for part x. Alright. Sine raised to a power. Very sus. What can we use? Can we use the Pythagorean identities, 1 minus cosine squared x? If we did use that, look at this. 1 minus cosine squared x, and then like sine x, sine squared x. The problem here is, there's a sine squared x somewhere, here. We can't turn that into something meaningful, like a sine x. Because if we used cosine x equals u, the negative sine x dx equals du. What we need is one sine, not a cosine. So that's going to be very difficult. What can we do in this situation? Well, we have to go back to an old friend of ours. Let me just bring it back. Here we go. Let's go back to here. Sine squared x is indeed equal to this thing. We have to use it again. So 1 minus cosine 2x. Let me just write it on the new one. Okay. So, know that a sine squared x equals 1 minus cosine 2x over... Oh, sorry, you can't see that. Let me just move it. Move it. Sorry. Wait, let me just... Yeah, you can see that. Anyway, sorry. We know that, can you see that? Yeah. Sine squared x equals 1 minus cosine 2x over 2. I hope you can see. Yeah, that's just below it. Should something there. Anyway, so sine squared x equals 1 minus cosine 2x over 2. That's all good. So we can express sine to the 4x as sine squared x then squared. We want to do that because we can use power reduction here in order to obtain 1 minus cosine 2x over 2 squared. This is now a trig function in terms of just 2, the power of 2. So that's good. Now what we can do here is to we can put 1/2 outside, but they're squared here, so it's going to be 1/2 squared or 1/4. Then the integral of 1 minus cosine 2x. What did they square? Dx. Forget the x here. 1/4, then the integral of 1 minus 2 cosine 2x plus cosine squared 2x dx. Another thing, cosine squared x is 1 plus cosine 2x over 2. Alright? So there's actually cosine squared x here, so we can use that too. Yeah. Let's turn this into this so we can solve it easier. So put 1/4 outside. 1 minus 2 cosine 2x plus 1 plus cosine. And the input here is 2x. So this is going to be 4x over 2. Because this is 2x, so it's double that. Double of 2x is 4x. So that's why that's 4x. Let's multiply, let's put 1/2 outside. So this becomes 1/8, and then this is 2, right? Minus 4 cosine 2x plus 1 plus cosine 4x. I did this by using our old friend again, multiplying both the numerator and the denominator by the same thing. So we multiplied 2 to the numerator and the denominator. The denominator went to the constant outside, 1/8. The numerator was multiplying everything else. So we have this, which is cool. And we can use the shortcut I taught you earlier. So, 1/8, and then let's just put a big bracket here. 2 dx 2x. That's the integral. Again, the integral of dx is equals to x plus c. Alright? Right? I don't need to to repeat that anymore, but yeah. The integral of dx, if you put a constant here like 2 dx, this becomes 2x plus c. So don't get confused. So 2x minus 4, and then the integral of cosine is positive sign, so sine 2x over 2, which is the this. You have to divide by that. Plus 1 is just going to be x, and then plus cosine 4x. Oh, not cosine. Sine 4x over 4. Again, because there's 4 in here, we have to divide by 4. Combine everything else. This 2x plus x becomes 3x. We have to divide by 8, and we get 3x over 8. Minus 4, 2, and then 8. So 4 times 4 divided by 8 divided by 2, that becomes so over 4. Sine 2x on the top. Plus, at the sine 4x term here, we multiply it by the 8, so we get sine 4x over 32. Let's see. Yes. Next question. Alright. Question number, what is this? 7. Did I stop numbering it? Anyway. Sine x plus tangent x over 1 plus cosine x. Now, what can we see here? Sine and cosine love each other. Tan x doesn't. So, let's just transform tangent into sine and cosine, so we don't get, in trouble. We put here sine x over cosine x over 1 plus cosine x dx. What we can do here to resolve the complex fraction is to multiply both the numerator and the denominator by cosine x. Again, my favorite technique. Alright? This results in sine x cosine x plus sine x on the top, and then Let's not distribute the bottom. You'll see in a second. Alright. Sin x on the top. Looks kinda... Hmm. I think we can do this. Sin x. We can factorize sin x. This becomes cosine x plus 1 over... Let's just put cosine x here. Then let's just flip the cosine x plus and 1 for no reason. And look at that. Cancel, cancel, whatever. This becomes sin x over cosine x, which we know is just tangent x. And if you know your integrals, this is just ln of secant x. Let's see. Nice. Question numero 8. Secant of to the power 6x dx. Okay. What we can do here is actually to separate secant squared with everything else. Why? You'll see why in a bit. Alright. We know this identity. Secant squared x minus tangent squared x equals 1. This brings us the fact that secant squared x minus 1 is tangent squared x. Sorry. Hold on. 1 plus tangent squared x. Sorry. I got that wrong. Alright. We have secant squared on one side. We have an even secant on on the other side. This looks like we could use a little bit of identities here. So, secant to the power 4x is secant squared x squared. Right? So, knowing this, we can replace the secant squared x with 1 plus tangent squared x squared secant squared x dx. We can actually substitute now. So, we can say tangent x equals u, and then secant squared x dx is equals to du. We have secant squared x dx equals du here. So, we can put du right here. And we can substitute everything else. So, tangent x becomes u, so 1 plus u squared here, squared. 1 plus u squared becomes the integral of 1 plus 2u squared plus u to the 4 du. Alright. From here, we can just integrate this. It's just in the normal power rule stuff. Sine u plus 2 over 3 u cubed plus u 5 over 5. Normal power rule stuff. No, not du. We can omit that actually. Why did I put that? Anyway. And let's see. And then we can turn everything back into tangent x. So tangent x plus 2 over 3 tangent cubed x plus 1 over 5 tangent to the power 5x plus c. That's the answer. Nice. Next page. Question number 9. Okay, sorry. Tangent to the power 4 of ln x dx over x. Alright. Well, what can we do here? I see ln x, I see x in the denominator. That's what I do first. Ln x is equals to u. Dx over x, which is the derivative of ln x, is equals to du. Dx over x is in there, so we can replace that with du and replace everything ln x with u. So, this is going to be tangent to the power 4 u. How can we do that? Well, we know that tangent square, secant squared x minus tangent squared x is equals to 1. Let's isolate tangent squared x. Well, this becomes actually secant squared x minus 1. You can't see the du. Let me just hold on. Sorry about my face cam here. My head is too big. Can you see it? Yeah, there we go. Dx over x equals du. You're not missing much. Anyway, so we know that secant squared x minus tangent squared x equals 1, then tangent squared x equals secant squared x minus 1. So how can we use that here? Let's separate the tangent to the power 4x with tangent squared x on one hand, and then secant squared x minus 1 on the other hand. Only this time we're actually working with u here, so let's just put u and everything else. And then the tangent, let's just distribute this in order to get tangent squared u secant squared u minus du. Let's just put du now, minus the integral of tangent squared u du. We have two things we now have to look out for. Okay, this one is easy. I think we can all see what's going on here. The derivative of tangent u is secant squared u, so we have secant squared u here, so that's good. That's good. Problem is the tangent squared u on the other side. We can use that again in order to, I don't know. So how can we use this? Well, let's just get down to business first. Tan u is equals to, let's say, another letter. What letter do you want? Letter alpha, because I want to be fancy. Secant squared du is equals to d alpha. Alright? If you see Greek letters in your mathematics, it's your high chance to run away. No, you just gotta, it's just another letter. So d alpha here. That's good. Minus, then integral of, let's put parentheses here, secant squared u minus 1 u. Alpha squared d alpha becomes alpha cubed over 3. Alright. For those of you who are wondering why it turned into alpha, it's because it's the letter I wanted to use. Alright. I just wanted to clear that up in case someone asks me why is it alpha. I always get that if I use confusing letters. Sorry about that. So we got minus, and then we can actually integrate this straight ahead. So the integral of secant squared u is tangent u. The integral of 1 is u. Right? I don't think I need to explain what the integral of 1 is, but let me just explain it. The integral of 1 du is u plus c. Alright? Some people have asked me about the integral of that. Like, it's just the integral of 1, man. It's just u. Anyway, that aside, let's put everything back together. Alpha is tangent u. So this becomes tangent cubed u over 3 minus tangent u plus u. We could put plus c here, but we need to put the ln x back in its place. So tangent cubed of ln x here over 3 minus tangent of ln x plus ln x plus c. There you go. Next. Ooh, this is gonna be hard, man. Alright. The integral of sine to the power 4x cosine to the power 4x dx. Woof. This is gonna be very technical. So, pace ourselves for a moment. What can we use here? I mean, if we try using cosine x as like sine x equals u, maybe, but there would be an odd cosine x, and we can't exactly turn that into sine if it's odd power, right? Here's what I'm mentioning. If sine x equals u, and then so there should be a cosine x dx here to serve as the sacrifice to the dx, so it could turn into du, right? But then this is just cosine cubed, so that's not going to work because I don't think you can transform cosine cubed into sine cubed unless you use like fractional exponents, and we don't want to deal with fractional exponents. We're dealing with trig already. So what can we do here? That doesn't involve that. Well, there's sine x and cosine x in the same sentence. And they have the same power as well. So what if we can use the double angle identity of sine 2x? We know this is 2 sine x cosine x, which have sine x cosine x same power. So I think we can use it here. Let's try using it. Sine x cosine x on its own is sine 2x over 2. Alright? We know this is a sine x cosine x both to the power of 4. This distributed. So this becomes sine 2x over 2 to the power of 4. We can bring the 2 to the outside, but there's power 4, so 1/2 to the power 4 is 1 over 16. Then the integral of sine to the power 4 to x dx. Let's let 2x equals u. Then 2 dx equals du. Dx equals du over 2. Why are we doing this? Let's just put 1/2 on the outside, so 1 over 16 times 1/2 is 1 over 32. Then sine to the power 4u du. I bring this up because we already solved this earlier. Let me just bring it back. So, there we go. Look at this solution. So, sine to the power 4x dx, our letter now is just different, it's just u, but the same answer, is this entire thing. So let's just copy it instead of solving it again. So I hate repeating myself. Okay. Anyway, so 3x over 8 minus sine 2x over 4 plus sine 4x over 32, right? So don't forget about the 1 over 32, that's important. Then 3x over 8, let me just review it again. Not that one, this one. Minus sine 2x over 4 plus sine 4x over 32. Okay. Minus sine 2x over 4 plus sine 4x over 32. Alright. Large numbers, but it's just powers of 2, so we can manage this together. This is 2 to the power 5, this is 2 to the power 3. 5 plus 3 is 8, so 2 to the power 8 is 256. So 3x over 256. 3x, not x, because now we're in the u. So this is going to be u. Minus 32 times 4 is 128 plus sine 4u over 1024. Let's see. We can replace the u with 2x here. So 3 times 2x is going over 256 is going to be 3x over 128 minus sine of 2, this should be u. 2 times 2x is 4x over 128 plus sine 4 times 2x is sine 8 to 8x over 124. That's the answer. Nice. Alright. Secant cubed 11. Secant cubed x tangent cubed x dx. What can we do here? If tangent x was u, then we need secant squared x. But we can't have secant squared x. How about this one? How about secant squared x tangent squared x, and then we can put secant x tangent x to the side. Secant x tangent x reminds me of secant x. What if secant x equals u? We have tangent squared here, but we can transform that into secant squared. x minus 1. So, here. Let, can you see that? Sorry. I'm sorry, I covered the question with my big head. Anyway, secant x tangent x dx. A bit cramped, but that will have to do. Let secant x equals u. Secant x tangent x dx equals du. That's the tool we have to use here. So integral at the end it's du, so du, and then secant squared becomes u squared, and then tangent squared becomes u squared minus 1. Right? Distributing together, we get u to the 4 minus u squared du. This becomes secant, no, not secant yet. U to the 5, this is just the reverse power rule, or the general power rule, or whatever you call it. U cubed over 3 plus c equals secant to the 5x over 5 minus secant cubed x over 3 plus c. That's it. Nice. The integral of e to the 3 secant 4x plus ln of secant 4x tangent of 4x. Now, this is a threatening integral if we don't know the rules. What are the rules that I am thinking of? What about this? We can separate the, since this is separated by plus in the exponent, we can separate that, the e's. So this is e to the 3 secant 4x times e to the ln of secant 4x tangent 4x dx. E and ln cancel each other out. This now becomes secant, integral first, 4x tangent 4x times e to the 3 secant 4x dx. Secant tangent, I smell an integral coming. So, what we can do here is to put 3 secant 4x be equal to u. We can do 3 times 4 secant 4x tangent 4x equals u. Secant 4x tangent 4x equals dx here. Dx. Sorry, I forgot that. And du over 12. So this this and that becomes du over 12. So 1 over 12 on the outside, and then du here, and that fulfills the du. Let me just put it closer since this is gonna be very small. E to the secant to the power secant 4x is e to the u. We all know this is just e to the u over 12 plus c. Now, u is now e to the 3 secant 4x over 12 c. That's the answer. If this sounds familiar to you, I don't know why. I don't know why it's familiar, but hey, that's the answer. And that's it for part 1, I think. Yeah, we're gonna proceed to part 2, which is integration by parts. Welcome back. Now, this next part is actually about integration by parts. So, how do we do integration by parts in this household? Well, we can do the traditional way, or we can use the DI method. First, you have to set up the table. DI. D stands for derivative, like d over dx. Integral stands for integral, like integral dx. And then we have to put plus, minus, plus, minus, plus, minus. Just alternating pluses and minuses until you finish. And when do we finish? Well, we'll have to determine that for later. Now, What do we put in D? What do we put in I? Honestly, that's up to you. But in this situation, let's put x squared in the D column, right? And let's put a to the x in the I column. Let's focus on the D column, the derivative column. The derivative of x squared is 2x. Derivative of 2x is 2. And the derivative of 2 is 0. And that's where we stop. Stop, number 1. When there is 0 in the column. Right? And I'm not talking like a Japanese Britannian rebel. No, I'm talking about the number 0. So if there's 0 here, stop. After that, we integrate a to the x. What is the integral of a to the x? Well, it's a to the x over ln a. The integral of that is a to the x over ln squared a. And then a to the x over ln cubed a. Next step is to multiply diagonally. Like this and that, this and that, this and that, and we stop at 0. So, positive x squared times a to the x over ln a minus 2x times a to the x over ln a plus 2a to the x over ln cubed a. Sorry, I put squared here. ln squared a here there. And then 0, there's nothing here. We just put plus c. And that's how you do it. Is it shorter? Is it longer? You decide. But I prefer this method because well, it's much shorter and easier than using the traditional method. Question number 14. Alright. 4x cubed cosine x dx. In this scenario, we can also use the DI method. This is integration by parts. Now, how do you decide what goes into D, what goes into I? For me, I just know what to put in D and I. But we can experiment. So if we put 4x cubed here and then cosine x here, let's see. 4x cubed, what's the integral? X to the 4, and then integral x to the 5 over 5, then x to the 6 over 30, and blah blah blah. The conceit of this is, well, it doesn't really end, right? The power just keeps getting bigger, bigger, bigger. The derivative is negative sine x, and then negative cosine x, and then it just repeats, right? So this is not really that useful of a start. So what we're going to do is to switch it up, just experiment, see what happens, you know. So in here you can put 4x cubed here, and then cosine x here. Look, the answer to this is now 12x squared. Then the derivative of that is 24x. Derivative of that is 24. Let's put minus here, plus here, and then that's 0. And that's where we stop since this is 0. Again, stop number 1, 0 in D column, or the derivative column. Again, not the rebel, not the Britannian rebel, but the number 0. Or Suzaku for that matter. Anyway, the integral of cosine x is sine x. No need to put plus c, just sine x. And then the integral of that is negative cosine x, and then negative sine x, and then cosine x. It's a cycle. Like a cycle. Cosine x, sine x, cosine x, sine x, cosine x, and whatever. So, next step is to just put the diagonal here. Ignore the 0 here. Alright? Now, what we can do is to multiply all this. So, don't ignore the sign. So, positive 4x cubed sine x. Minus minus, that is plus 12x squared cosine x. Plus minus, that is minus 24x sine x. Minus plus, that is minus 24 cosine x. Plus c, because it's finished, and that's the answer. Miles easier than using the other traditional method. Question number 15. Integral e to the 2x sine 3x dx. We can use the DI method for this one, but what does it entail for us? Let's see. I want, what do you want in D or I? We can experiment. Let's say we put e to the 2x here, and then sine 3x here. This becomes 2 times e to the 2x. And this becomes negative 1/3 cosine 3x. Yes. This becomes, the derivative is 4e to the 2x. And then negative 1/9 sine 3x. Whoop! E to the 2x here, sine 3x here. E to the 2x here, sine 3x here. Stop number 2 is when there is repetition. There is repetition e to the 2x sine 3x, e to the 2x sine 3x. Now, you can say, well, there is 4 and negative 1/9 here, so technically it didn't repeat. But I can say to that, it's just a multiple. It still repeats in a cosmic sort of way. You can put the constant multiples outside. So anyway, you'll see what happens here. We do the normal thing, this and that, but for this, we actually have to put the integral sign, and then we have to multiply both of these. Alright, so let's go here. Let's actually write this. E to the 2x sine 3x dx is equals to plus minus, that is negative 1/3, there's 1/3 there, e to the 2x cosine 3x. Minus minus, that's plus 2/9. 2 times 1/9 is 2/9. E to the 2x sine 3x. Right? And then the integral of the integral of 4/9, negative now, because there's a negative there, so let's put negative on here. And then 4/9, let's actually put 4/9 outside. E to the 2x sine 3x dx. Here and here, they look very familiar. So let's transpose this to the other side. Or if you don't know how to do that, or if you're confused by it, I get confused by it all the time. We can add 4/9, the integral of e to the 2x sine 3x dx here, and then add the same thing on the other side. Alright, this, they cancel each other out because, 0. Not durable. 1 plus 4/9 is 13/4. There we go. And then, let's just copy the right hand side. Sans this. Plus 2/9 e to the 2x sine 3x. What we can do here is actually to multiply by 4/13. Why do we do that? Because it nullifies the 13/4 on one side. So we get the integral of e to the 2x sine 3x dx, which again is the thing that we wanted to solve earlier, is now equal to 4, then negative 1/3, 4/13. That becomes 4, negative 4/39, e to the 2x cosine 3x. Plus 2 times 4 is 8, and then 9 times 13 is 117. E to the 2x sine 3x. Let's see. That's your answer. Very cool. And nice. Alright, next question. Number 16. This is actually very familiar because we solved this earlier. Sine 3x sine 6x dx. We remembered earlier that we used the uh, the the sum identities, the addition identities, sorry, of trigonometry. The sine, the cosine A plus x and cosine A minus B. A plus B and A minus B, you know. This time, we're going to use integration by parts. So how can we do that? Again, let's just the DI method that. D and I. What can we put in D? What can we put in I? Honestly, it's up to you, but I can just put sine 3x here and then sine 6x here. Why did I put that here? Because I just wanted to test it if there's something that goes on it. You can test sine 6x on the D column, sine 3x in the I column, but that's up to you. And then, the derivative of sine 3x is 3 sine 3x. The integral of sine 6x is negative 1 over 6 sine 6x. And then this is 9 sine 3. Not sine, sorry. I forgot about this. It should be cosine. Sorry. Cosine 3x. Cosine here. Then negative 9 sine 3x since cosine negative. Okay. So this is going to be negative 1 over 36, I guess. Sine 6x. Yes. Now, how do we go about solving this? Well, again, sine 3x, sine 6x, again, stop number 2, repetitions, is in full force today. So we can use that. Diagonals, positive, negative becomes, let me just put the original integral again. Integral of sine 3x, sine 6x, dx. Right. This becomes negative 1 over 6 sine 3x cosine 6x minus minus becomes plus 3 over 36 cosine 3x sine 6x plus the integral of 9 over 36. Let's put the 9 over 36 on the other side. Sine 3x sine 6x dx. We just transpose this thing to the other side, the second integral, we get 1 minus 9 over 36, since the factor here is 1. So 1 minus 9 over 36, that's going to be 27 over 36. Okay, simplest terms, 27 over 36 is 3/4. Okay, so on one side, let me just sorry about that. Oh god, oh beans. 3 over 4 on the other side. Integral of sine 3x cos sine 6x dx. Alright, this becomes negative 1 over 6 sine 3x cosine 6x plus this can be 1 over 12 cosine 3x sine 6x. God. Alright, multiply both sides by 4 over 3, so we can nullify the 3 over 4. Finally, we go here. Integral of sine 3x sine 6x dx. 4 over 3, this 4 over 3 times 1 over 6, that becomes like 2 over 9. Negative 2 over 9. Yeah. Sine 3x cosine 6x. Then 4 over 3 times 12, that becomes 1 over 9. Cosine 3x sine 6x. Then plus c for good for good measure, and there we go. So now you ask, is this the same as the one earlier? And to that I say yes. There's sine and there's still a bit of sine 3x cosine 6x there. That's the DNA of the answer. But if the answer turns out to be different, if you graph it in Desmos or something, it will be separated by a constant. So because the constant could be different, yeah. So there you go. It's still the same answer. Don't be scared of that. It's just a different form. Question number 17. integral of 5x to the 4 plus 4x squared plus 2x ln x dx. What can we di here? Use the di method. What can we do here? One thing of note. ln x. What is the integral of ln x? If you don't know the integral of it using the integration by parts, it's kinda difficult to think about it. It's difficult to use it even because there's another ln x in the integral. What if we put ln x in the d column instead? And then we put everything else in the I column. Would that work? Let's experiment. Again, don't be afraid to experiment. If it works, it's good, right? So this becomes x to the 5 plus 4 squared is 4x cubed over 3 plus x squared. I think we can stop here. Because stop number 3 is if the column is solvable. What do I mean by solvable? You will see why in a bit, why this is considered solvable. Again, let's do the normal thing. So integral, let's not put it there. We put x to the 5 plus 4x cubed over 3 plus x squared, and then multiply by ln x minus the integral of 1 over x times x to the 5 plus 4x cubed over 3 plus x squared dx. If you distribute 1 over x here, this becomes, I just copy it like that, minus the integral of 1 over x times x to the 5 is x to the 4 plus 4x cubed over 3 times 1 over x is 4x squared over 3. And the x squared times 1 over x is just x. And this is what I mean by solvable. This entire column here, you can actually solve it using something other than integration by parts. You can use the reverse power rule here. So that's good, right? So let's rewrite x to the 5 plus 4x cubed over 3 plus x squared, then ln x here, minus the integral of x to the 4 is x to the 5 over 5. The integral of 4x squared over 3 is 4x cubed over 3 times 3 is 9. Plus x squared over 2. Plus c. Tada! That is the answer. So you can experiment a bit and you can find something solvable in the end. Alright? You just gotta trust your gut instinct sometimes. X e to the x over 1 plus x quantity squared. This is question numero 18. The x. DI method. Is this applicable by DI method even? Let's try. Let's try experimenting. Let's try putting x e to the x here and then 1 over 1 plus x quantity squared in there. First of all, let's put the second problem. What's the derivative of x e to x? I think you need to use the product rule. So let's go back to the past to the power rule. When we use that, x e to the x again. This is u. This is v. U prime. This is u. This is v. So x e to the x, and then derivative of x is 1, derivative e to the x is e to the x, then crisscross, and then we get x e to the x plus e to the x. We can factorize e to the x here in order to get e to the x plus 1, or we could put 1 plus x, commutative property of multiplication. So 1 plus x times e to the x, again commutative property. What is the integral of 1 over 1 plus x quantity squared? Is that something fancy? Let's try testing. Let's test it out. Let x plus 1 or 1 plus x equals u. Dx equals du, so nothing changes with the dx. Over u squared. U squared is negative u to the negative 2. So this should be negative 1 over u. That should be the integral. So negative 1 over u is 1 plus x. Look at this. 1 plus x, 1 plus x. I think that's solvable. Let's try. Again, this we do. So negative x e to the x over 1 plus x. Nice. Plus the integral of e to the x, then 1 plus x over 1 plus x. I keep switching it around, but it's the same thing. This and that cancel each other out. We get ditto. Plus integral of e to the x dx. Oh my god, I think I know what that is. Rewrite. Plus e to the x. Let's see. That's the integral. Right? By smartly using the DI method to our own advantage, we were able to make it easier for us. Yeah. 19. The integral of cosecant to the power 5x dx. Now this is a bit difficult, so buckle up. Buckle. What do we put in D? What do we put in U? We know that cotangent x and then d over dx. This is negative cosecant squared x. Correct? So there's cosecant to the power 5. Maybe we can split that into cosecant cube and cosecant squared. But cosecant cube doesn't have a good good analog to cotangent. Let's try using the DI method for this one, or integration by parts. I just call it the DI method. So, cosecant cube x here, cosecant squared x here. Minus column. The derivative of that is 3 cosecant squared x times negative cosecant x cotangent. So negative here, then cosecant x cotangent x. It's just overlapping there. So the integral of cosecant squared x is negative cotangent x. So let's erase this one. The diagonal, it's now ruined. Diagonal, so we first put negative cosecant cubed x cotangent x. Then the integral of this row here, so negative, negative, negative is going to be negative. Integral of 3 on the outside. Alright, let's put 3 on the outside. Cosecant squared x. No, actually, look at this. There's cosecant cubed x. There's now 2 plus 1. So then cotangent squared x, since there's now 2 of them. What we can do here is actually to turn the cotangent into something cosecant adjacent. So cosecant, remember, cosecant squared x minus cotangent squared x equals 1. And then we get cotangent squared x is cosecant squared x minus 1. Correct? So, we put negative cosecant cube x cotangent x minus 3, then the integral of so this becomes cosecant squared x minus 1. This becomes cosecant to the power 5x minus cosecant cube x dx. Now, negative 3 cosecant to the power 5x, we can put that to the other side since this cosecant to the power 5x dx there as well. Just waiting. So, this is 1. Then 3 going there becomes 4. So, 4 integral cosecant to the power 5x dx. Okay? 1 plus 3 is equals to 4. You know, all that stuff. Negative cosecant cube x cotangent x. And then Minus minus is plus 3, then the integral of cosecant cubed x dx. Our good old friend cosecant cubed x. Now, if you've watched previous videos of mine, you may have remembered secant cubed x. Now it's cosecant. Same thing, not that much harder, but it's tricky to get a hold of it. But it goes like this. We do the same thing we did earlier, but this time with cosecant. So, di again, we have to do it again. Alright? Be patient with me on this one. Okay, cosecant squared x here, and then the remaining cosecant here. Negative cosecant x cotangent x as the derivative, and the integral is negative cotangent x. So, let me just put this here without the 3, so so it doesn't get confusing for now. Negative cosecant x cotangent x. That's that. And then we have to integrate this row. We have to integrate that, right? Negative, 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 that's negative. And then the integral of cosecant x cotangent squared x. Again, this is cosecant squared x minus 1, right? So we get negative cosecant x cotangent x minus cosecant cubed x plus minus 1 dx. Let me just see if it checks out. I think it checks out. So now we can bring the cosecant cube to the other side. This becomes 2 cosecant cubed x. There's cubed here. Hold on, dx equals negative cosecant x cotangent x minus minus is plus, then integral of dx. Now, if you don't know, the integral of dx is equals to x plus c. I think you don't know. Yeah, it's just x plus c. So it's something. Yeah. Yes. So this becomes. Oh no! Wait! I'm so dumb. Sorry. This actually becomes cosecant. Sorry. I'm so sorry, man. I'm too deep into this. This is not the x. This is cosecant. I thought it was wrong. It's nothing like that. Okay. I apologize. Now, the integral of cosecant x. What is the integral of cosecant x? It's not. It's like secant, but the harder version of secant. Like, it's actually. Let me just copy this. No dx. Plus ln of cosecant x minus cotangent x. Alright. You have to multiply this, the cosecant x minus cotangent x, the numerator denominator, and then you can find, that. So that's all good. But there's 2 in here, so we have to multiply by 1/2 on both sides. That's easy. So negative 1/2 here, 1/2 here, and there we go. Let's go back here. So let's just bring this entire thing up. Bring all that. Bring all that here. There we go. Hey, what up? What do you know? So let's bring all that back, and we know that cosecant cubed x dx is this entire thing. So let's put it back. Equals negative cosecant cubed x cotangent x minus 3 times 1/2, 3 over 2 cosecant x cotangent x plus 3 times 1/2 is 3/2 ln of cosecant x minus cotangent x. There we go. There's still 4 here, so we need to multiply by 1/4 on both sides. Alright? And finally, the answer is Negative 1/4 cosecant cube x cotangent x minus 3 over 8 cosecant x cotangent x plus 3 over 8 ln of cosecant x minus cotangent x. Let's see, and that is the answer. Wow, so long, right? That's what you do with that one. Okay, now we proceed to the third part of this, which is integration by substitution. But not just any integration by substitution, it is advanced integration by substitution. So let us proceed to it. Question number 20. The integral of ln x over square root of x. Square root of x looks annoying. It looks out of place. I don't like it that much. So why not get it out by substituting that as u. Square root of x is not equal to u. We want to isolate x here, so x equals u squared. Why? Because if you take the derivative of this becomes dx equals 2u du. So this means we can just replace the dx with 2u du. Put the integral sign here. Ln x becomes ln of u squared, since x is now u squared. And then square root of x becomes u. Cancel. We get 2 on the outside, and then ln u squared du. Now, if you know your logarithmic properties, you know that you can bring that power back of 2 here. So we get 2 times 2 is now 4, and then ln of u du. Ln of u. How do we solve that? Well, we can use the DI method. Ln u in the D column, like earlier. And what's in the I column? That's the thing. Well, there is 4 here, so we can put 4 there. Integral of 4 is just 4u, and then integral of ln u is just 1 over u. So this is solvable now, right? So we get initially 4u ln u minus integral of 4u over u du. U and u cancel each other out. 4 du, the integral is 4u. Then 4u ln u. U is square root of x. So we are back with 4 square root of x times ln square root of x minus 4 square root of x. That is not yet the answer, because ln square root of x is just x to the power 1/2. So we can do 4 times 1/2 square root of x ln x minus 4 square root of x, which is now 2 square root of x ln x minus 4 square root of x plus c. That's the answer. Nice. Question number 21. Integral of the square root of e to the x minus 4 dx. Good. Now what about this? Square root of e to the x minus 4 sounds difficult. What if we do this? Square root of e to the x minus 4 equals u. Why do we do that? I don't know, just experiment with it. See where it goes. You can't make an omelet without shooting a few eggs, so to speak. So e to the x minus 4 equals u squared. So e to the x dx equals 2u du. 2, that's 2. Problem is we don't have an e to the x. So do we go back to the drawing board? Maybe not. Notice, e to the x is equals to u squared plus 4. We just transpose the 4 to the other side. Now we have an interesting scenario. If we isolate dx, we get 2u du over e to the x. The e to the x can be substituted as u squared plus 4. This becomes e to the x, square root of e to the x minus 4 becomes u multiplied by this is du, du. Dx is now 2u over u squared plus 4 du. 2 can go outside. u squared goes here, and u squared plus 4 goes here. Now, we can make use of my second favorite technique in mathematics, which is to add something and then subtract something at the same time. Because 4 minus 4 is 0, and that is my truth. This is equal to 2 times, we can separate the fractions here, u squared plus 4 over u squared plus 4 minus 4 over u squared plus 4. Now you can use another technique. I think it is the long division on this one, but I don't think this is necessary for this particular one, so we'll just do that. But you can absolutely use the other one, which is the, yeah, you can use that one. Long division. Now, separate again. 2 integral of u squared plus 4 over u squared plus 4, that becomes just 1. So it's just du. Minus, and then 2 times 4 is 8. Integral of du over u squared plus 4. Now, let's just switch it out so you can see it better what this is. 4 plus u squared. This could be 2 squared plus u squared. And there's something about arctangent that makes this better. If you're integrating this form, the answer is 1 over a arctangent of u over a. Right? Don't forget to see. So we can use that form to solve that. So 2u, which is this one, minus 8, and then times 1/2 arctangent of u over 2 plus c. U is, let's go back, u is e to the x minus 4, so this is now 2 to the power, square root e to the x minus 4. 8 times 1/2 is 4. Arctangent of u is square root of e to the x minus 4 over 2 plus c. That is the answer. Nice. 22. dx over x to the 4 over 5 plus x to the 6 over 5. I think there's a common factor in there, so let's try. What could we do here? That over 5 thing is bothering me. Why not put it to rest by substituting it into u? We can take the 5th power to both sides. So this becomes x equals u to the 5, and then dx is equals to 5u to the 4 du. Alright? So let's do that. 5u to the 4 du on top, and then on the bottom is u to the 4 plus u to the 6, since this is 4 over 5 and 6 over 5. Alright? Let's factorize everything. So u to the 4 du over, on the bottom, u to the 4, then 1 plus u squared. Something's familiar. U to the 4, they cancel each other out. Whatever. So 5 integral du over 1 plus u squared. And look at that. That is the basic arctangent integral. And you can use u plus c. U is 5 arctangent u is x to the 1 5, so 1 5 c. That's the answer. Nice. Question numero 23. dx over x plus square root of x. Alright. What can we do here? That square root of x is bothering me again. This is another fraction. I hate the square root. Anyway, so we can use square root of x as the u here. What does that entail? X equals u squared now. Right? So dx is equals to 2u du. We can replace the dx with the 2u du over X becomes u squared. Square root of x becomes u. Nice. 2 square u du. We can factorize this in order to get u. Then u plus 1. It's similar to the one before, but a bit different looking. Now we get 2, then du over u plus 1. And then this is just the ln, so 2 ln of u plus 1. U is of course square root of x, so we get 2 ln of square root of x plus 1 plus c. That's it. Nice. Last question, 24. Integral of e to the sine x dx over secant cubed x. What did I tell you earlier? Sine x loves cosine x, secant loves tangent. These things do not love each other very much. So how about we put that secant in its place? Since it is in the denominator, putting it in the numerator will make it cosine. So cosine cubed x e to the sine x dx. Oh, dx. Yeah. Sine x equals, if sine x equals to u, cosine x dx equals to u, it's cosine cube. We can turn the cosine squared into 1 minus sine squared x. Alright, let's put e to the sine x here, and then cosine x right here. Alright, so sine x equals u, cosine x dx is equals to du. This one is du. The integral of 1 minus u squared here times e to the u. We can use the di method on this one. Good lord. So what do we put in d? What do we put in I? Well, for e to the u, it doesn't matter where we put it, but it matters what we put on the other side. So maybe 1 minus u squared belongs here, maybe e to the u belongs here. So the derivative of this is negative 2u. Derivative of that is negative 2, derivative of that is 0. And we stop there. Stop number 1 when the d column has a 0 in it. E to the u here, e to the u, e to the u, e to the u. I think everyone knows what that is. So we multiply all of that. Positive 1 minus u squared times e to the u. Minus minus is plus 2u e to the u. Plus minus is minus 2e to the u. And that's the c. U is sine x. So let's combine all that together. 1 minus u squared plus 2u minus 2u e to the u. Let's see. Combining, we get negative u squared plus 2u minus 1 e to the u. This sounds awfully familiar. Yes, it is indeed negative of x minus 1, or no, u minus 1, u minus 1 quantity squared e to the u plus c. Right? Yeah. You can get that. That's magic, right? That's absolutely magic. Nice. And then what we can do here is to substitute it back to sine x. So negative u is sine x. So negative sine x minus 1 quantity squared e to the sine x. Let's see. And that's a good answer. So that's all I can do for now. I hope you can pass your midterms exam for Calculus 2 because I know who's watching this. People were reviewing last minute. I'm going to review for other subjects, and while you're at it, thank you for watching this video, and I hope my last videos have helped you. This is probably a 2-hour video, and the last video I posted 6 hours. Very long videos. But I love doing this, so I'm doing it for you guys. So thank you. Thank you for watching, and I'll see you in the next video where I'll post a 10-hour video next. Most of you probably won't watch it fully, but yeah, see ya.